let's continue to the some practical algorithm we can use to solve this constraint optimization problem. There are two. Actually, the concept is exactly same, and somebody called this penalty method. The idea is transform our constraint optimization problems into unconstrained optimization problem. Because unconstrained optimization is much more easier to solve and take care in terms of computer algorithm. There is two different approaches. First one is exterior penalty method. The second one is interior penalty method. Keep that in mind. These two approaches is not the only algorithm available out there. There are numerous other computer algorithms available, but this two is chosen because it's most simple and straightforward to understand. Okay. Okay, let's begin with our original problem. Consider our problem key is constraint optimization problem, which is minimization of some function fx subject to an equality constraint and that is the typical form of our constraint optimization problem. And we denote the feasible reason as S. It's nothing more than the X which satisfy all the constraints. The idea of this penalty method is extend this feasible reason into in a constraint optimization problem, our only feasible reason is S. However, in this penalty method, our feasible reason becomes this. Exactly same as unconstrained optimization. How this is possible? Well, we modify the function itself. I mean the objective function. Okay. Let's say there is some function like that. And I don't know, maybe our feasible reason is something like this. We are only subject to find inside of this enclosed region. And let's assume that our objective function is look like this this is the global minimum, and let's say this is the contour of our objective function. Okay? I'm not sure, but maybe our minimum will be around somewhere here, right? Right? And in previous class, we discussed about the optimality condition. If the point, if the current point satisfies this KKT condition, then we know that this is the local minimum of this constraint optimization problem. However, if you look at the KKT condition, there are lots of gradients. All the gradient for the objective function, all the gradient for the equality constraint, and all the gradient for the inequality constraint, which is very much computationally expensive. So, idea of this penalty method is like this. Let's see this part. Let's put our eyes here and look in this direction. Okay? Then the function will look like that's our cutting plane here. We are looking this direction, and our function will be look like this, right? And here, the global minimum here, and we are only allowed to move in this here because it's out of our feasible reason, right? Question so far? The idea of this penalty method is we put penalties and at the same time extends our feasible reason into this real number reason. Okay? What if we change our objective function like this? In the feasible reason, our objective function is exactly same as the previous objective function. But when it go further out of this feasible reason, what if the function behaves like this, or probably this, or sometimes, it's possible. Then, without this feasible reason S, we will eventually end up somewhere like here, or here, or here, which is the third case is exactly the local minimum we are looking for. Okay? If we modify our objective function like this red line, then we don't have to anymore consider this feasible reason anymore. Okay? That's the exterior penalty method. That's the exterior penalty method. And it's almost similar. That's the original, our fx. And what if we change our objective function fx like something like this? Not exactly same here, but very close to like this. or, you know, something like this. Then, if we succeed to change our f(x), or objective function like this red one, the minimum value of unconstrained optimization will be somewhere like this, okay, which is very close to our constrained optimization problem. Then we don't have to consider anymore this feasible reason. The difference is that we are only dealing with interior of this feasible reason, right? In this method, nothing is go beyond this feasible reason. So we call this as a interior penalty method. And somebody called this as a barrier method. Because we put very severe barrier which prevent our point to approach to these boundaries of our feasible reason. So that's the barrier. Okay? Question? The key point is by changing the f(x), we'll transform our constrained optimization problem into unconstrained optimization problem. Because unconstrained optimization is much more easier and computationally inexpensive compared to this constrained optimization. Okay? Okay, let's talk about this barrier method first. I finally understood that you guys don't like mathematical proofs. So I bring up some example. Okay? Okay, let's assume our problem is very simple like that. X1, xy is a plane. That's our objective function, and we'd like to minimize it. And there is constraint, such as subject to and we have two inequality constraint and one objective function like that. Okay, let's apply this barrier method first. Interior penalty method. The idea of this penalty method is by modifying the objective function, if this is the feasible reason, we are changing the function like this. How these values are different? Well, we need some kind of parameter R, and based on this R value, you can determine how much this new transformed objective function approaches to the real one. So, let's say this phi is the new modified objective function. And, this large X is this point, it's a function of the points, at the same time a function of some penalty parameter. And it is exactly same as this f. Plus, minus so penalty factor of to remove any. Okay. Since in our problem definition we said that there is a m different inequality constraint. So this means for every inequality constraint we take the inverse value, not exactly, reciprocal value, and we sum up all these reciprocal values. Okay, so let's look into this one. Since these are inequality constraints, okay, so if we are inside of this inequality, the feasible region, for example, if we are around this area, okay, then since the inequality constraint should less than or equal to 0, so it is in minus value, okay. However, when we approach it to the boundary, such as we approach it to the boundary, this g value approaches to 0, okay. When this g value approaches to 0, this reciprocal value will goes up, right? Which makes this kind of characteristic. If it approaches real close to this, then it theoretically it goes to the infinity, right? The reason we use minus is because GIX is always in the negative side in feasible region. So by adding all these reciprocal values of each possible inequality constraint, we are making things like this, which make a very, very severe barrier, which prevent your point not to come too close to this barrier boundary. Okay? So that is the definition of our phi function. Once you change your objective function in this form, then you don't have consider the constraint optimization anymore. Okay. Okay, utilizing this form of function, we can write our function phi for this specific question problem. It is that's our new objective function. Okay. And next step is we are supposed to find the minimum of this using what we have learned. Okay. It's a very simple unconstrained optimization problem. How do we determine or how do we find the local optimum? We can we can run the some of the algorithm we've learned, or because this is very simple analytical form, we can use necessary optimality condition, which is gradient is 0, which is we are supposed to find the solution of these two equations. Del P over del x1 is equal to 0. Del P over del x2 is equal to 0. If we can solve this problem, then we can express our local optimal point in terms of R value. You know, based on this R, we can control how much this new new objective function approaches to this value. Okay. Okay. This one is one minus x1 square is equal to 0, and if you do your mathematics, the x1 should satisfy this equation. And for the second equation, it is 1 minus r over x2 squared. And if you solve this equation, this x2 should satisfy this equation. Okay? And from this condition, we can rewrite this equation in terms of the R. So, x1 star is the local minimum of the x1 value of the local minimum, and it is function of R. Okay? This is and the second equation, x2 star function of R is did I mention that this R should be positive number? R should be positive number always to make this function works. Okay, this equation tells us that if we choose this x1 star and x2 star, then our new objective function p will have its local minimum, right? So, our minimum value of this p is also a function of R, and what we have to do is just plug this x1 star and x2 star back into this p equation, and if we do that, minus this form of equation will tell you that based on your R, selection of R, there should be a variety of series of this new function p, right? P is dependent on this R value, and your local minimum is also dependent on your R value, right? But anyway, we found this one, okay? Okay. Very brief question. What if this R value increase? Is it go in this direction or in this direction? Let's assume you put 1 instead of R. And let's assume this is P1 when R is equal to 1. What if you put the R is equal to 100? Then your value will around somewhere here, right? So, but we'd like to find this exact solution. How? By taking limit value of this. If R approaches to 0, your minimum value will approaches to this value, theoretically. So, the next step is to obtain the solution of the original problem. This. So, this is minimum value of our original function is nothing more than limit value when R approaches to 0. Okay? And the xy location is also nothing more than this one. If you take the limit approaching R, make your R approach to the 0 value, then you will have the minimum value of the original problem and minimum, the local minimum location, like this. Okay. I've calculated a simple table based on your R value and x1 star, x2 star, P and F. If you take the 1 as the R, this is actually, and this is 1, and this is, and if we take the limit, so make this reduced by 10, and let's take this 0.01, let's point at 0.001, then and eventually if we take the infinity, sorry, not infinity, 0, then it's a you can clearly see that as this R value decreases and approaches to 0, the value approaches to the exact values. I mean, this value is, you can easily solve it without any knowledge of this algorithm or something like that. You can easily solve the exact solution by plotting it. And this is the exact solution, and it matches to the values when we take the limit of this b. Okay? Okay, algorithm. Algorithm is just exactly same as what we've done so far. Let's take an initial feasible point. And let's call this is x of 1. And this initial feasible point should, because we said it's feasible, it should satisfy all the constraints. Okay? This should satisfy all the constraints. But one more limitation is, since we take the reciprocal form of the inequality constraint, this feasible point should satisfy with strict inequality. In another word, even though the problem form says this is our inequality constraint, but for this initial feasible point, it should be a strict. Because if it's equal to 0, then we cannot make a phi. Okay? And we randomly take R1, a positive value, a 1 or something, and let's set K is our stem number is equal to 1. And the next step is simple. Minimize phi. And in order to minimize this phi function, you can use any unconstrained optimization algorithm. obtain your minimum. And number 3, test the optimum. Test if this one is actually the optimum, then stop. Otherwise, find the value of the next penalty parameter. Usually, your next penalty parameter is some constant value times the current parameter. And as you know, C is always a positive number. And finally, increase your counter by 1 and update your initial point with current optimal point and go to step 2. Okay. It looks like very simple. However, in step number 2, it depends on your choice of unconstrained optimization method. If you take the Newton method, it is nothing more than just run the Newton method once again here. So even though we are simplifying our constrained optimization problem into unconstrained optimization problem, however, this constrained optimization problem is always more complex and take more time compared to this unconstrained optimization problem. Okay, the exterior penalty function method. You know, compared to the barrier method or interior penalty method, this one is somewhat easier in terms of programming. But it has some kind of weak point. For example, if this is your feasible reason, and if this is your objective function, interior or barrier method are changing your problem into this and find this minimum, right? Which satisfy all your constraints. Whatever you choose, your local minimum is within your feasible reason. Okay? But when it comes to the penalty method, sometimes your penalty will behave like this. If you choose a right penalty, then you will have this form of penalty, so ends up with the exact local local minimum. However, if your penalty looks like that, your local minimum are sometimes out of your feasible region. That's the weak point of this exterior penalty method. Anyway, computationally it is more easier because we don't take any reciprocal form of the constraint function. Let's say this is still the same problem, and unlike the interior or barrier method, now the exterior penalty method utilizes a somewhat different p function. Until this part, it's the same. However, it's also penalty parameter summation of all the inequality constraint, and it's a bracket function. And also looks like this. This R sub k is positive penalty parameter and this Q here is non-negative constant. And we utilize this bracket function here. This bracket function is defined as the maximum function among your function and zero value. And it is really easy to implement in computer code. There are usually max function is there, right? So the return value is like that. It will return g sub j x if this g sub j x is greater than 0. And it will return 0 if this g sub j x is less than or equal to 0. So max function is just return the largest among these two. Okay? And this is the function. Okay, let's look at this in terms of this problem. If g sub j, in this problem, g sub 1, if this g sub 1 value is less than 0 or equal to 0, which means your point x is now satisfying the g sub 1 constraint. Okay? Then this bracket function will return 0. So you don't have to consider this part for the g1, right? But if this at your specific point x, if your g sub j is greater than 0, then it will return the function value. So it comes, there is some value, and powered to the q and multiplied by this positive penalty parameter, which means if it returns 0, then constraint is satisfied, right? And if it returns this g sub j, constraint is violated. Right? You know, if the constraint is satisfied, then we don't have to consider that constraint anymore. For example, if we are around in this region, we don't have to consider that constraint. It's just same old unconstrained optimization. Okay? What if another drawing, the original one, like this, and let's say this is your feasible region, and if your contour of the function is look like that, then okay, this is your G1 and G2 hypothetically, and let's assume you're around this point, then you're satisfying G2 and G1 at the same time. Okay, then your objective function is just like this f(x), and all you have to do is just solving the unconstrained optimization problem because you're inside of this region, right? Okay, but when it goes to by steepest descent algorithm or something like that, if you move to somewhere here by your iteration step, then at that time this G1 kicks in to apply heavy penalty to prevent your point not to approach this. Okay? So usually this positive penalty number is determine the shape. At the same time, your Q determines the shape of this exterior penalty. For example, if your penalty, let's say this is the G1, and you have a first order function, and if we take the Q is equal to 1, then your penalty function will be a straight line or something. Okay? You can change the slope by modifying this RK value. Right? If you take the Q is equal to 2, then for this G1, your penalty will be quadratic function. And you can modifying the slope of that quadratic function by changing this R sub k value. So idea is if you go outside of the outside of this feasible region, severe penalty will be applied. That's the idea of this exterior penalty method. Question? Okay, let's see the algorithm. First one, starting from any x sub 1 and a suitable value of r sub 1, and your counter is set as 1. Second step is find the vector x sub k star which minimize the function, the phi function here, Okay. And the third step, check if the point x of k star satisfies all the constraints. If yes, stop. The algorithm is a little bit different because in exterior penalty function, there is possibility that you will end up outside of this feasible region. So you have to check this point is actually inside of the feasible region. Step number 4. If it's not inside of the feasible region, choose the next step is you choose a higher or greater value of penalty parameter. And then increase the counter and go to step 2. And usually you take the similar approach but you can utilize any other method to find a new r sub k plus 1. The thing is like that. For example, your q or r sub k should be randomly chosen at the initial stage. If you know the problem characteristic, you can choose this value more cleverly. However, it's just initial guess. Based on that, sometimes if your q value or r sub k value is not great enough, not large enough, you will end up outside of this feasible region. Then, by choosing parameter, if you choose a larger parameter, whatever the q is, usually the shape will goes up, right? Then, which will increase the penalty when you go outside of this feasible region, which will guarantees to go to this point. So iterative process. Okay? And usually people tend to take this value as 1 or 2 because if you take a higher value, then it is computationally expensive, right? If you take 100, well, that's nice, but you have to multiply the same function in 100 times in your computer algorithm. If you, for example, this kind of problem, everything is in first order, but if you'd like to utilize a Newton method in this step number 2, it is just the unconstrained optimization. In Newton's method, you got to calculate the Hessian. And if you choose number 2 for the q, then you can easily calculate the Hessian for this specific problem. Then number 2 is your natural choice. Okay? But if you just want to use the steepest gradient method, then don't have to use number 2. That's too much. It is just fine to use the number 1 for this Q value. This Q value can be wisely chosen by yourself based on the knowledge of this optimization problem. Okay? Okay, let's do the example once again with the same problem. It's a same function. And from this problem, we can write the p function as let's assume we started from the initial point. So let's make it x sub 1, which is x1 fx plus the penalty function times penalty parameter times the greater value among 0 and 1 minus x, 1, which is the first inequality constraint. And for this problem, let's take 2 for this Q value. So I'd like to have this nice, smooth, and quadratic shape out of this penalty. And for the second penalty, let's okay, that's our new p function. And according to step 2, now we are supposed to find the minimum value of this unconstrained optimization problem. And like the previous example, let's utilize the necessary optimality condition to calculate the optimum, local optimum. Okay, the necessary optimality condition is gradient of this phi should be 0, right? Which is exactly the same as del p over del x1 should be 0. And at the same time, del p over del x2 should be 0. And if I evaluate this equation, del p over del x1 is x1 minus plus 1 over square minus 2r that's the first optimality equation from optimality condition. And if I do the second thing is okay, now we have 2 equations, and we have to find the x1 star and x2 star, and this x1 star and x2 star should be described in terms of the r penalty value. Okay. from the first equation, this one, we can rewrite the equation like and from the second equation, we can rewrite the equation like which means among the smallest of these two, x1 plus 2, x1 plus 1 squared and x1 plus 1 squared minus 2r 1 minus x1, among the smallest two, it should be equal to 0. From the second equation, among these two, the smallest one should be equal to 0. Because we are minimizing this one. Okay. What if this is equal to 0? Then x1 is equal to minus 1. If x1 is equal to minus 1, then it will violate the first inequality constraint. And this one, what if this is equal to 0? Then it's fine. It does not violate any inequality constraint. So from this, and if you calculate it, we know that x1 is equal to and from the second equation, 1 cannot be equal to 0. So one possibility is this one should be equal to 0. So okay. Okay, from these two equations, the solution of the unconstrained optimization problem is okay. And in the interior point method or barrier method, we take the limit value of r and make this r value approaches to 0. However, in this our exterior point method, as r increases, the slope increases, which means if you take the limit value as r approaches to infinity, our point, our unconstrained optimization point will ends up here. Okay? So, for now, it is same to take the limit value, but the r value now is approaching to the infinity. Okay? So, the local optimum point is nothing more than limit value r approaches to the infinity. It's x1 star r. And and this is 1, and x2 star is limit if r approaches to infinity, x2 star r, and this is 0, and the minimum value of our function is also same as limit of this phi is like that. Okay. Okay. I once again took the calculation of this value. If I take 1 and 10 and 100 and 1000 and infinity eventually, this x1 value moves to 0.23607, 0.83216, 0.98039, 0.998, and the exact value is 1. For the x2 star, it's minus 0.5, minus 0.05, minus 0.005, minus 0.0005, and eventually the exact value is 0. And phi value is 0.9631, 2.3068, 2.6249, 2.6624, and the exact value is 8/3. And this f value is 0.1295, 20001, 25840, 2.6582, and exact value is 8/3. Okay, as you can see, as the r value increases, it approaches to the exact values.